Good morning, students. We are discussing on railway and airport engineering. Well, in the previous lecture, we have discussed about a parameter which affect the geometric design of the railway track. Okay, and that is the super elevation, or we can say cant. Well, there is also a possibility at points and crossings or at the time of turnouts that the particular train has to divert his track, or it has to take the right turn or the left turn. Well, at that particular point, well, there may be possibility that a train has to take the turn on the curve side at right or left, and at that moment they might have need to change the track. So at that particular point we have to provide a super elevation on a two different line, but we cannot provide the super elevation on both the lines. So at a particular line we have to give the super elevation, and the another line we have to compensate that elevation. Okay, and this type of concept is known as the negative super elevation. Well, what is negative superelevation? On a curve site, there may be two diversion, or the two line needs to provide. Okay, the one which is known as the branch line, and the another one that is known as the main line. Well, on the curve, always a branch line meets the main line at certain places. Well, at that time, the outer rail of the main line of curves meet the inner rail of the branch line. Well, as the super elevation is provided on the main line, the outer rail of the main line is at a particular higher level than that particular inner rails, and the inner rail of the branch line will have to be kept at the higher level than the inner rail. But here, as the outer rail in the branch line is at the lower level than the inner rail, and that is known as the negative super elevation, or we can say the negative cant. Well, under certain condition, it is not possible to provide the equilibrium cant. Well, as shown in this figure, a branch line diverges from the main line. Yes? Well, here in this figure, you can see AP and BQ are the inner rail and the outer rail of the main line respectively. And that BD and AC are the inner and outer rail of the branch line. Yes? Well, there should be some conditions has to be satisfied where you provide such type of two different lines, or where you need to provide the negative super elevation. That is, by considering the main line, the outer rail BQ must be at the higher level than the rail AP, as at the main line that outer rail should be at the higher position. Yes. So in another word, we can say the point B should be always at the higher level than the point B. And considering the branch line, the outer rail AC must be higher than the rail BD. Well, in another word, we can say the point A should be higher than the point B. Well, how is that possible? That for the main line we have to compensate that B should be higher than A, and at the branch line we have to kept point B at the higher elevation. So that is definitely a contradictory conditions. Okay, so these two contradictory conditions cannot be satisfied at the same time within a one layout. So instead of outer rail AC on the branch line being higher, it is always kept lower than the inner rail BD, and in that type of cases, the branch line curve has the negative superelevation. Understood? That is the negative superelevation, and therefore the speed on the both line must be restricted at particularly on the branch line. So this is the actual concept of providing the negative superelevation. Okay, we cannot provide a rise on the same time at both the rail lines. Okay, so what we do, we provide the higher elevation on the main line, okay, and we kept at lower situation on the branch line. Okay, well, some of the method of working out the speed on the main line, the branch line, and the negative superelevation on the branch line will be clear from that some of the steps. Okay, so which help us to working out on the speed at the main lines. The first, that is the equilibrium superelevation or the cant on the branch line, has to be calculated. Okay, and to calculate that equilibrium superelevation, we have already done in this in the previous lecture. Okay, so we have the formula that E is equals to gv square upon 127 r, where the superelevation or the cant we got would be in the millimeter, g is a gauge distance, v is the speed of the train, while r is the radius of curve. Clear? The second, that is the permissible cant deficiency, is deducted from the equilibrium cant. Okay, and that equilibrium cant we have already obtained in the step number 1. Okay, so now the second step that we have to follow to deduct the cant deficiency from the equilibrium cant. Now the thing that you have to remember, that is at particular gauge distance, the cant deficiency for a particular speed limit, that is up to 100 km/h, is been already defined. So that is for the broad gauge 76 mm, middle gauge 51 mm, for the narrow gauge that is 38 mm. Okay, so keep this in mind. The third step, that is finding out the negative superelevation, and for that we have this equation that negative superelevation would be always equal to the difference between equilibrium cant and the permissible cant deficiency. Okay, so from this equation we will able to get the negative superelevation. Then the next step to be followed, that is the negative superelevation should be also equal to the maximum superelevation that is permitted on that particular main curved track. And then we have to find out the speed on the curved track, okay, by using the formula E is equals to gv square upon 127 r. Okay, so from here we can able to get the value of v. So this is how we can working out on the speed or at main lines. Okay, so this was about the negative superelevation. Now let's see the example which is based on the negative superelevation. The question is, a 5-degree curve diverges from a main curve of 4 degree in an opposite direction in the layout of a broad gauge. Well, if the speed on the main curve is restricted to 54.33 km/h, determine the speed restricted on the branch line. And we have to assume the cant deficiency as a 7.5 cm. Well, if this cant deficiency is not given, then we have to follow the permissible cant deficiency up to the speed of 100 km/h. Okay. Well, here we are given with the degree at main line and the branch line. Now let's discuss about the given data. That here at the main curve we are given with the data of a 4-degree curve. Okay, also we are given with the speed on the main curve, that is 54.33 km per hour. So based on this data, let's find out the super elevation, that is equivalent super elevation. While for the main line, from the degree of curve, we can able to find out the radius. So d is equals to 1720 upon r. From that we will able to get the value of r, and which is 430 meter. The speed of the train at the main curve is been given, that is 54.33 km per hour, and the gauge distance for a broad gauge, that is 1676 millimeter. So based on this data, the equilibrium cant E should be GV square upon 127 R. So the equivalent cant, that is 90.59 millimeter. Now, after this elevation, we have to find out the negative super elevation. Okay, and for that we need to go with the cant efficiency. So on the broad gauge, the cant efficiency is 7.5 centimeter. Now, if we convert it into millimeter, 75 mm is the cant efficiency that we have to provide on the main track. So the equivalent super elevation that we obtained, that is 90.59 minus 75. So it means that we have to provide a cant on the main track of 15.59 millimeter. Now this particular cant that we have to provide on the main line. So at the branch line, that negative super elevation that we have to provide is minus 15.59 millimeter. So for the branch line, a permissible cant efficiency again, which is already given, that is 75 mm. Well, here we have to add this elevation into cant efficiency. So the cant for the permissible speed should be 75 plus that negative super elevation, but the value of that negative super elevation is minus 15.59. so 75 minus 15.59, which is 59.41. okay, well, r, that is 1720 upon d, degree at the branch curve is been given, that is 5. From that the r is 344 meter. From that we can able to obtain the speed on the branch line, and that is 39.35 kilometer per hour. So according to this data, the speed that should be restricted on the branch line is 39.35 kilometer per hour. Well, another example, a 5-degree curve diverges from a 3-degree of main curve. In reverse the direction in the layout of the broad gauge yard, if the speed on the branch line is restricted to 35 km per hour, we have to determine the restricted speed on the main line. While in the previous lecture the data of main line was given, but in this example we are given with the data of the branch line. Okay, so starting the example from the branch line, the degree, that is 5. Okay, so from that the radius of the curve is 344 meter. The speed on the branch line, that is 35 km per hour, and as the broad gauge is being used, the G value would be 1676 millimeter. So according to that data we can able to find out the equilibrium cant, and that E which is 47 millimeter. Well, here the cant efficiency is been not mentioned. So on the broad gauge up to 100 km per hour speed, we have to take the cant efficiency as a 76 millimeter. So the negative super elevation is equals to equilibrium cant minus the cant efficiency. while equilibrium cant, which is 47 mm, minus 76 mm, while this value comes as a minus 29 millimeter. So on the main line, we have to provide a negative superelevation of 29 millimeter. Here the negative superelevation comes in the negative value, so that will be reflect on the main line in the positive value. Okay, so for the main line, the negative superelevation, that is plus 29 millimeter. Okay, so the theoretical cant is equals to 29 plus the cant deficiency, that was 76. So total theoretical cant, that is 105 millimeter. While for the radius, the degree of curve on the main line is 3 degree. So the radius of that curve would be 573.33 meter. Based on this data, we can able to find out the value of speed, that is V, and which comes 67.54 km per hour. So according to this data, at the main line, the restricted speed should be 67.54 km per hour. Clear? So that is the examples based on the negative superelevation. The next topic, that is widening on the curves. Well, on a curved track, due to the rigidity of the wheelbase, when the flange of the outer wheel of the front axle strikes against the outer rail, then the outer rail wheel of the rear axle bears a gap with the outer rails. While due to the coning of wheels, the outer rail travels a longer distance compared to the inner wheel. Yes, so however, this becomes impossible for the vehicle as a whole system, since the rigidity of the wheelbase causes the trailing axle to occupy a different position. While in an effort to make up the difference in the distance traveled by the outer wheel and that inner wheel, the inside wheels slips backward and the outer rail or the outer wheels skid forward direction. Well, a close study of running of vehicles on curves indicates that the wear of flange eases the passage of the vehicle around the curve, and as it has the effect of increasing the gauge, this widening of the gauge on a curve has in fact the same effect and tends to decrease the wear and tear on the both wheel. Okay, now how much extra width for this we have to provide on the curve sides, that can be obtained from this formula, which is W is equals to 13 into B plus L square upon R, while this extra width will be in the centimeter. Talking about this notations, B is the rigid wheelbase in meter, capital L is the lap of flange in meters, R is the radius of the curve, that will be also in meter, and the value of lap of flange can be obtained from another formula, that is 0.02 under root h square plus dh. Well, again, this d and h is nothing but diameter of wheel and the depth of flange respectively. Okay, so from this we can able to find out that how much extra width we have to provide on that particular track at the curve side. Clear? So this is about the widening on the curves. Okay, well, with this we are concluding our today's lecture. I hope students you understand this topic properly. Thank you so much for your kind attention. I will see you in the next lecture with a new topic. Thank you.